stuff that I wish to cover. I don't know if I didn't make a list actually of stuff that we skipped, but I have one slide lying around where I can show you some of the cool stuff that we did not touch if I have internet access. So there's, let's see, I hope this shows up on something. So this is a small fraction of stuff that I did not cover, but means this is just a brief list. I just wanted to not make several slides. I have previously shown this slide also, but for those who are interested in viewing, just getting a crude idea of a little bit of how big optimization itself is beyond the kind of optimization we saw for machine learning. There's a small little encyclopedia, 4,500 pages from Springer. It's not a very useful encyclopedia except the table of contents that shows you list of topics. You don't need to read the documents, but getting topic labels is good enough to gain an idea. But sometimes it's good to go there for fishing to discover if the kind of problem you are investigating, if it has been looked at in other parts of the world. We did, Alex did mention in the beginning briefly, but we did not spend too much time really studying convex relaxations of difficult problems. Sometimes coming up with good convex relaxations is an art, and one of the reasons why semi-definite programming itself became so popular within computer science. It was very popular in control systems and other areas, but it became ultra popular in computer science after the seminal paper of Roman and Williamson, which Alex covered. And that's just one example of relaxation. Before that in theory CS, people used to study linear programming based relaxations and so on. And these days, relaxations based on sums of squares and other stuff coming out from convex geometry, that's quite popular and so on. But we didn't get to see any of that, unfortunately. And we did not devote time to software. Maybe Alex might have mentioned some systems ideas, but really, ultimately, to the world of optimization, ideally, it's a very, very applied world. And as you might know, ultimately, even when it comes to deploying optimization or to deploying machine learning, large part of the success lies at the systems level, of getting it right at the systems level. So there's various efforts at CMU, at other universities here and around the world at getting the systems layer correct. But anyhow, the stuff that I would have liked to talk briefly was more related to convex geometry, some connections to probability theory, which we skipped. We only lived in finite dimensional optimization, which is somewhat unfortunate. I didn't talk at all about robust optimization and various flavors of stochastic programming and so on. We looked at only stochastic optimization, the simplest level, the kind that is used in machine learning, but there's something like multi-stage stochastic programming in other areas, optimization where the constraints are not explicit but just probabilistic and so on. So all sorts of cool stuff that we skipped out. And I mentioned only very briefly one little thing about optimization in non-vector spaces. And that was in the very beginning when I told you about a notion of convexity which holds in general metric spaces, not only on manifolds. And when I mentioned to you some of the theory related to Perron-Frobenius theorem and optimizing using fixed point theory, there we are optimizing on a special kind of manifold which is just non-negative cone. But we didn't really get to look at all of those. But someday when I develop these ideas further, you may be interested to learn about those, including optimization over pretty cool metric spaces like metric space of trees or metric space coming from some kind of structured graphs. Those are not numbers in R to the n. They have geometric structure, and that geometry does not directly embed into Euclidean space, but you can still directly optimize in that space because the notions of convexity, which I mentioned from the very beginning, convexity just measures this, how far internal you are on a line type of property, that generalizes to all sorts of spaces. So just to tell you that all you saw in this class, as far as optimization is concerned, is a very small fraction, but you saw nevertheless some things which are cutting edge and of publication, means current interest, like some things related to optimization that I mentioned to you in the class. They are things that are, say, published this year, last year, and so on. So it's not, so you did get to see plenty of that, but the world of optimization is much larger. So eclectically, as I find maybe closer connections to machine learning and so on, I'll put up slides or material related to that. And other than that, I'll just let's conclude the class by thanking all my students here.